Okay, well, we've kind of moved quickly through previous sections, but what I'm this section probably will spend a much larger portion of the time on. And what these are doing is basically taking the parent function and shifting it horizontally or vertically, reflecting it across either the X or Y axis, and then stretching or shrinking the function depending upon the values compared to the parent function. So the first thing you do is you identify what the parent function is, and then you see if there's any actually you really look at the reflecting first, and then you look at shifting, and then the non-radiated transformations, stretching and shrinking. So here's an example. We have the red function, which is y equals x squared. Now, if you put the parabola in standard form, this is what it looks like. Now, we're not showing you how to put something in standard form. We're just going to give it to you in standard form, and then you can make the appropriate moves. Because what you're going to do is you can take the parent function, just going to move it. So the size, the relative position of the points stays the same. It's just that the, say, this part, which is called the vertex, gets moved. And the term that's not inside the parentheses, that tells you how much it's shifted in the y direction. So it's pretty easy to do that. So plus 3 means that you shift the origin, the vertex, 3 units in the y direction. So if it's plus 3, move it up 3. Now here we actually take the negative, or we take its x minus the number. So if it's minus 2, we actually just use positive 2. If it's positive 2, then we use minus 2. And that tells us how much to shift horizontally. So if we have negative 2 here, we're going to shift to positive 2 in the x direction. So combination positive 2 in the x and plus 3 in the y puts the origin of the, not the origin, but the vertex of the parabola here. And then the other parts relative to this new vertex are the same distance. So if you can see, I go over 1, up 1 here. So I'd go over 1, up 1 there. I go over 1, up 1 here, over 1, up 1 there. If you go over 2, 1, 2, you go up 4. So you go over 2, up 4, go over 2, up 4. So that's how they work with parabolas as far as shifting is concerned. We're going to talk about shifting first, but then we'll talk about reflecting. Okay. Now, so the question is, what is the anchor point? That's kind of where you do all your calculations relative to that point. So for a cubic function, let's look at this on one page. For a cubic function, it's this point. So everything's relative to that point, the origin. It's usually the origin. Here, square root function, it's this point. So we're going to shift that point and then draw everything relative to that point, the new point. So like for example here, we'd go over 2 and up 8. Now if this thing got shifted over here, the anchor point would move, but then relative to this anchor point, we'd still move over 2 and up 8. Let me just demonstrate that. So let's say the center, the anchor point is moved here. And you can see if I go over 1, I move up 1. You can see the scale is different. It's 2, 4, 6, 8. Here it's 1, 2, 3, 4, 5. So this is 1 unit. This is 2 units. Or one. This is 1 unit. Sorry, this is 1 unit, and this is 1 unit because I'm halfway between these two. So 1, 1. So what I would do is I'd go over 1, up 1, like that. That would be, this point would correspond to that. And if I go the other direction, I go over 1 and down 1. So I take my new anchor point and I go over 1 and down 1, which would be that point. So these two are the same points relatively speaking, these 2 points are the same, and then this point goes with that one. Okay. So what happens is if you draw using these 3 points here, so it's going to come in, it's going to go like that, and then it'll go up. Now this one, for example, if we go over 3, so we go over 1, actually if we go over 2, we're down 8. Here's 8. So with the new position, here's my new, so we go over 2, down 8. So that's 2, 1, 2 in the X direction. 8 is 2, 4, 6, 8. So that's that point and that point are corresponding. So what'll happen is this thing will come down through this, go through that point, and then it'll drop off like that. And this one was off scale, so this one will actually go up here, and since we're shifting, it probably goes up to this point 10. And if I took the blue curve, and it's, you know, I've not done a very good job of drawing it, but if I took that, I could set it over top of the other curve. So that's all we're doing is we're taking the original curve, we're just shifting everything up by the appropriate amount. So the reciprocal function, so this is y equals 1 over x. Here's the anchor point. So everything, all these points are relative to the anchor point. So if we shifted this over 2, up over 1 and up 1, so let's say my new anchor point is here, what happens is everything gets shifted this way and up that way. So you can see relative to the original anchor point, if I go over 1 and up 1, I have a point on this curve, so I'd go over 1 and up 1. And I do the same thing down here to go over 1, down 1, over 1, down 1. And so what would happen is we drew in a kind of a pseudo coordinate system here. So instead of this reciprocal function being symmetric around here, it's going to be symmetric around here. And then you can draw this thing out. So here this curve approaches the x-axis. Here this curve is going to approach this line, x equals 1, and then it'll come up and it'll have vertical asymptote here. Likewise, this will come from down through there, and then it'll approach that vertical asymptote. And again, if I take these two, if I take this thing, I should be able to shift it over and it should match up with that. And if I take this, shift it down like that, you know, they should match up exactly. So we're not changing the relative position of all the points. Now, if you stretched or shrunk it, then yeah, it does change that. But for the reflection as well as for translation, you're just moving things around. And finally, this anchor point again would be the origin. So if I move the origin, if I moved it over this many units in the x direction, this many units in the y direction, let me just go ahead and, so what I'm going to do is I'm going to just draw right over top of this, the original parent function, like that. So what would happen is if I made a copy of that thing, cloned it, what I would do is I put that, so that line ends there, and then this line, clone it, that would go over to here. So that would be that would be the original anchor point. This is the new anchor point, and you just shift everything over and up. And they should look pretty much the same. Okay, so that's the anchor point and translating. The next thing is reflections, and it depends upon whether it's an odd function or an even function. Well, actually, it doesn't. what it matters is whether if you're reflecting across the x-axis, what you do is you take the original function, you just put a negative out in front. So instead of x squared, we have negative x squared. And that's different than if we reflect across the y-axis, we have negative x, the quantity squared. So the negative is inside the actual function. So what I'm really doing here is I'm taking x and I'm squaring it. So if the negative sign is in the parentheses, then it's a reflection across the y-axis. If it's outside the parentheses, or we don't show any parentheses here, but if I did, this is outside the parentheses, this is inside the parentheses, this is outside the square root, this is inside the square root, this is outside the absolute value, this is the inside value. Here, it doesn't really matter, because this negative sign here, which is outside, if I drew a vertical line like that, what would happen is I could take that and move it inside with the x, and so those, whether you reflect across the x or y axis, it basically looks the same. So some of them look the same. This one doesn't look the same. This one, whether you have it outside or inside, doesn't matter, because if you cube -1, you still get a negative out front. Here, if you square a negative, you get a positive, which is different than a negative if this thing is squared. So it depends upon which function you're trying to reflect. Now what we have here is kind of an example of where we have both shifts and reflection in it. It says always do the reflection first. So what we have is the original parent function, and then we have this more complicated function. So we have a negative inside here, and which is going to affect the translation. This negative outside is going to affect the reflection. So what we do is we first take the parent function and we put a negative sign in front of it. That first process here reflects this function around the which axis? Well, let's look at our little cheat sheet here. So if the x negative is outside here, then it reflects it across the x-axis. Okay, so that's going to reflect it across the x-axis. Then this part is going to tell you that because this x is positive inside here, then it's going to you're going to have a shift in the positive 2 units because we have x minus the shift. And then finally we add this last term, which is to shift it in the y direction. So let's see if I have a graph here. Okay, so this is the same thing. Yeah, let's show how this works. So we're going to put a piece of graph paper up. So I'm going to do the parent function in black. The parent function is y equals x squared. So you have go over 1 up 1, over 2 up 4, over 3 up 9. If you go -1 squared is positive 1, -2 squared is positive 4, -3 squared is positive 9. So that's the parent function, like that. Okay, now the first thing you do is well, actually I'm meant to do this one here because that's different. So let's move this up one. Okay, so we're going to do this one first, where the negative sign's out front. So what that says, negative, we're going to take the parent function, we're going to flip it across the y-axis. So what that means is you still have the same origin because we haven't translated it anywhere. But instead of going over 1 up 1, we go over 1 down 1, over 2 down to 4, over 2 down 4, and then over 3 and down 9. So you can see, relative to the origin, everything's a mirror image. So we get something that looks like that. So So that's the reflection part. Now once it's reflected, then we're going to move it to this says to move it 2 units in the x direction, positive, and this one says to move it 2 units in the y direction. So let's what we'll do here is we'll try to just grab this red function. So I'm going to group that together. So that's grouped. So now I should be able to move that thing. So what you do is you take the reflect thing and you move over 2 and you move it up 2. And that's what you get. So that's the final answer. Now if I go to my graphing program and I put in this equation, we'll see how it looks. We'll put in the parent function first. So we have y equals x squared. And then if we put in minus x squared, that'll be the flipped part version. So let's just look at that first. So so you see there's the parent function and there's the reflected function. That's what we did first. Okay, now what we do now is we take the negative of x minus 2 squared plus 2. So that's negative x minus 2 quantity squared plus 2. It says we're going to shift it positive 2 units in the x direction, positive 2 units in the y direction. And there it is. So that's what I have. That's the curve right here. And I could probably go back to this. So you can see that looks, actually what we need to do is zoom out to about 10 units in the x direction and about 10 units in the y direction. Okay, so you can see those match up pretty closely. Okay. Now here the negative, we have a negative inside the parentheses, but besides having to do the reflection across the x-axis first, what we do is we have to factor out a negative sign inside the parentheses. So what we'll do is we'll have negative the quantity x plus 2 squared plus 2. So what I've done is I've factored out negative 1 for both of those terms. So if I multiply this back out, I'd have negative 1 times x, which is negative x. I have negative 1 times 2, which is negative 2. So that's the form we need to look at. This negative sign has to be out first. If you have a negative sign in front of x, you want to factor that out of both terms. So what that means is that besides reflecting across the x-axis, or y-axis, because the negative's inside the parentheses, is we're going to shift. The shift is going to be plus or minus 2 in the x direction. Because what you do is you take this number and you take the negative of that. So that shift is negative 2 in the x direction. And you also have to shift plus 2 in the y direction. So those are the two shifts. Okay, so let's add a page and get some graph paper. So again, we're gonna draw our parent function, and I'm just drawing the points on the parabola. So here's your parent function. Now, in this case, what happens is this negative here flips it across the y-axis. So this goes over there, and that goes over there. So when you actually draw the curve, it looks exactly the same. It's just that the actual trace is the same, but when you go to when you go positive 2 in the x direction, you'll have positive 2 plus 2 is 4, and then you'll have the whole thing positive 4 become negative 4, and then you square it, which becomes positive 16, plus 2, which is positive 18. Okay, so in this case, the rotation across the x-axis really didn't change the curve, how the curve looked. So again, we can, if we grab that curve and stick it together so that I can move it like this. So all I have to do now that I've rotated it, is I just have to shift it negative 2 in this direction, in the x direction, and positive 2 in the y direction. And that's what it should look like. So again, I'm going to go here, and what we're going to do is we're going to take the negative sign, and we're going to put it inside. So it's negative, that's the original function before I factored out. So we had negative x minus 2 quantity squared. Okay, so that's the original graph. So it's negative x minus 2 quantity squared plus 2. I graph it, and you can see that's where the function is. So this corresponds with that. So it did work out correctly. So let's continue on. This is some examples using the square root function. So what I have is just a second. So over at the right I have the parent function, which is the square root of x squared, square root of x. So what I'm going to do is I'm going to just kind of sketch over top of this thing just to make a copy of this that I can move around. So there, you can see now I can grab this thing. So that's the square root of x, and I can move it, I can rotate it. So what we do is we start with the parent function, which is the square root of x. And then all we have here are just translations. So the two translations, we got the x translation, we got the y translation. And it's always x minus, we'll call it h. And then this part here we would call k plus k. So there's some argument, it could be parentheses, it could be square root. So plus 2 is negative h, or h, negative h, or h equals negative 2. So it's going to, that means this is going to be shifted 2 units to the left. So that's 2 units to the left. Now this is the term that's not inside the argument of the function is the k, and it's plus k. So in this case we'd say plus k is equal to negative 3, or k is equal to negative 3. So that would mean to shift it down 3. So negatives down here. H is negative 2. So it means to the left. Okay. So we take our parent function and our anchor point is the origin. So we're going to move this point to the left 2 units and down 3 units. And so that would be the resulting function. Now, of course, because we have more space now, we could extend that off in that direction. And if we look at this, if we plot the parent function and then we put a semicolon square root of x plus 2 minus 3, and we plot that, you can see that it's been moved over 2 to the left, down 3. Okay, so let's move this back up here. Start it. So we'll go to the next problem. So here we have the negative sign out in front of the square root. So we still have the same translations. So we have shift x 2 to the left because of the negative, and shift y 2 down, 3 down. Okay, so as long as we have a positive number in here in the argument of the square root, then everything's fine. We just do the normal kind of thing. Now what the negative sign means there, let's go back a few pages. The negative outside the argument. So we had the negative somewhere here. Oh, I guess I didn't. That must. Oh, here it is. So here we have the negative outside the argument. Negative outside the argument, which means reflection across the x-axis. So to reflect it across the x-axis, what we're going to do is we're going to reflect it, so the mirror image, using my flip. Here it means flip top to bottom. And so it's flipped, and then I bring the anchor point down to the origin. So that's all I've done here. The first step is just put the negative sign in front of the square root of x. So this is the square root of x. This is negative the square root of x. Then I do these two shifts. I go to the left 2 and down 3. And that's my final. So that curve here is negative the square root of x plus 2 minus 3. And again, I'll pull up my graphing program and we'll put that in there. So it's negative the square root of that, and I graph it. And you can see that there it is. It's flipped over the x-axis and then shifted. Okay, so here we go. Let's move this back up, and we'll flip it back again. So we'll flip it up and down. So then I'll just put it right over the top of there. Okay, now the negative sign's inside the square root. So what I do here is I factor out a negative sign inside the square root. So you have negative x, and you factor negative out of both terms. So it's x minus 2. So negative x plus 2 is negative x minus 2. The term outside the parentheses is unaffected. So these are equivalent to each other. So what this means is I'm going to do a y-axis reflection. But my shifts in this case, what I have is it's x minus h. So negative h equals negative 2, or h equals 2. So in this case, we have an x shift of plus 2, which means to the right. And our y shift is still the same because that's outside of the shift. I think I put shirt there. Shift. Okay. The y shift is negative 3, which means down. And this inside the square root means y-axis reflection. Okay, so let's do that. So we take our parent function. In this case, we don't shift up and down, we shift left to right. So, we flip. Flip left to right. So you can see it's flipped, and then I bring the anchor point, which is the origin, so that they match up. So that curve there is the square root of negative x. And then I take that and I shift it 2 units in the positive x direction, 3 units in the negative y direction, and there I go. And again, I'll pull up the graphing program, and the second function is not negative the square root of x, but square root of negative x and plus 2. Okay, so I graph that, and what I should see is that, which I do. See, notice it's flipped across the y. Whoops, it's flipped across the y-axis, and then it's shifted to the right 2 and down 3. Okay, let's move that back again. So we'll flip it back the other way. Put that over it. Shift it back to the origin. Get rid of this little doohickey thing. Okay, so now the last one is we have 2 shifts. We have 2 reflections. We reflected across the x-axis and the y-axis, but again, we need to factor out the negative sign. So we get the negative the quantity 2x minus 2 minus 3. So the first thing we're going to do is we're going to, so the steps, it doesn't really matter which we do first, but you start with a parent function. Then we're going to go negative the square root of x, and then we'll go negative the square root of x. So this one is going to be an x-axis reflection. So let's grab my function. We'll flip it vertically. So that's my x-axis reflection. Then I flip it left to right. That's my y-axis reflection, but again I bring the anchor point back. So that's that, negative a negative square root of x. And then the shift is the same as the previous one. So because I have negative 2 here is equal to negative h. H is positive 2, and I have a negative 3k. So what I'll do is I'll go positive 2 in the x and negative 3 in the y, like that. Finally, we go back here and verify it. So I have negative the square root of negative x plus 2 minus 3. And I graph that, and there you go. You see, that's the right places. Flipped around the x-axis and around the y-axis. Now you could flip around the y and then the x. Doesn't matter which order you do it in. You still end up with this function going like that. Okay, so we did all that. Okay. Yeah, let's just look at a couple examples here. So this is the parent function. That's the reciprocal function. So if I were to do this, if I did negative 1 over, oh, actually I've got to draw the reciprocal function. So let me just plot it and then I'll grab it. So I'm going to go back here. I'm going to write in just 1 over x, which is my parent function. Graph that. There you go. And let me grab the camera. Okay, there we go. So I think I'll just get rid of that picture. Drag that over here. Okay, so there's the reciprocal function. Now let's just do a few different translations. So you get negative 1 over x plus 2. So again, normally you have x minus h. So in this case, negative h equals positive 2 or h equals negative 2. So that means shift x 2 units in the negative direction, which is to the left. So again, what I'm going to do is I'm going to draw, kind of trace over this. Trace over this bottom part. Not the best drawing in the world. And what I need to do is grab these two and group them together. Because relative to each other, they stay the same. So now I can take that. So what's going to happen here is this curve stays exactly the same, but it's going to be shifted 2 units to the left. So I take this and I move it 2 units to the left. So 1, 2, and you'll notice that if I draw an axis here and an axis there, you can see everything's moved over 2 units. Okay, so you can imagine that if I have f of x equals 1 over x minus 3, in that case, negative h is equal to negative 3, or h is equal to 3, which means I would shift it the other direction. So here's the, let me get rid of that little accidental thing. So here's the parent function, and then I just move 3 units to the right. For some reason, these have become detached. So let me group those together again. Okay, so I'd move this thing 1, 2, 3 units to the right. And you kind of tell because the vertical asymptote here is going to be at x equals 3. So if you draw a vertical line at x equals 3, we see that the vertical asymptote is there. Okay, now if you did f of x equals 1 over x plus 2 minus 5 or minus 3. Again, this does the x shift, and so it'll shift left 2 units, just like it did up at the top, and it will go down, since we have a -3 here, down 3 units. So we moved it. Which way do we go? Oh, we got to go this way. So move this. So here's the parent function. Move 2 units to the left, and then move it down 3 units. So 1, 2, 3. And again, let's just check this out. So put a semicolon in there. So what we have is 1 divided by, and put in parentheses, x plus 2 minus 3. And let's see what it looks like. So there it is. You can see that it's the same as that. Okay. Now let's actually look at this. So let's go back to if I put a minus sign in front of here. So it's minus 1 over x plus 2. Let's see what that does. Okay, so that the negative in front of the argument does that. It does a reflection. So let's look at that case. So what I'm going to do is let me add a page here. So if I were to have the function is equal to -1 over x plus 2, I'm just going to do it without any y-axis, any y-direction translation. So this is, again, outside the argument. The argument is the denominator. So that should mean it's going to be a y-axis reflection. I mean x-axis reflection. So what I do is I take my thing here and I would flip it vertically up and down. So I get that. So let's just see if that's true or not. So I'm going to go back, take this -3 out of there, and just plot that. And yeah, actually, what did I do here? Oh yeah, so that's the reflection part, and then you translate it 2 units in the x direction, in the negative x direction. So then you end up like that. Okay, so there. Is that right? Actually, I did the wrong thing there. No, wait a second. Let's see what we're doing here. So so I don't think I actually ever. What did I? Rotated that across the x-axis, and then I was going to shift it. Maybe I got it wrong here. Make sure I did this right. -1 over x times x minus 2. Okay, so that should be okay. I might have just remembered the wrong. So if the negative is out in front of the argument, let's go back here. So the argument here, it's an x-axis rotation. So why isn't that doing what I thought it was going to do? Well, I think it did. Let's go back here. Okay. Well, part of the problem is I reflected the wrong thing. That's why. Okay, I reflected the red curve. Okay, so there we are. Now, what I need to do is grab onto hopefully the black one. And actually, this thing is still upside down. I need to rotate this around a few times. I think I did it too many times. Let me undo things here. There we go. Okay, we're back to where we started. Now what I need to do is make sure I click on the black curve. Hopefully I did that. And then, okay, so now what we do is we reflect across the x-axis, which is up, down. And then we shift that 2 units to the left. So 1, 2. Okay, now let's look at the graph. See if that matches up. Yeah, there we go. So it was me. I made a mistake when I flipped the red curve instead of the black curve. That's why it didn't make sense. So what's the opposite? What is the, if you had rotation or reflection across the y-axis? Well, if you had 1 over negative x plus 2, so now that negative sign is in front of the x in the denominator. So what you would do is you'd factor out a negative, so you'd have negative x minus 2, negative the quantity x minus 2. So again, you're going to, in this case, you're going to shift it to the right, and you're going to flip it around the y-axis. So let's take this thing back again. Move that back here, flip it across back to its original position, which is up, down. Okay, so there we are, back to the original curve. Okay, so the first thing we do is we reflect across the y-axis. So let's grab that and flip left to right. So that's that. And now because I have x minus h, we'll have negative h is equal to negative 2, or h is equal to 2, so that means we move this way 2 units. And then we double check it here by inputting that. So we come over here, instead of have negative 1 over x, we have 1 over negative x plus 2. And we graph that, and you see there we go. The blue curve is like the black curve. Okay, moving on to the next thing, which is x cubed. So again, I'm going to go to this graphing program. I'm going to plot x cubed. Show what that looks like. Okay, so that's x cubed. And we're going to zoom in a little bit in this way, just so it's a little better, a little different. Okay, so now we're going to take a picture of that. And where's my camera? There it is. Go over here, take a picture of that thing. Okay, so that's y equals x cubed. So we'll do the same kind of thing. We'll look at some different examples. So let's say we have y equals x minus 2 cubed plus 3. So all we're doing is translating this thing. So let me sketch over top of it. There's my parent function. Okay, so now I have a function I can move around. So, we have x minus h, so negative h is equal to negative 2, h is equal to 2. Here we have k, k is 3, so what that means is shift right 2, because I have h is positive 2, and shift up 3, because this is 3. And so I just take the parent function, I just shift it, so that the anchor point here is the origin. So I can move that origin point 2 units to the right, and then up 3 units. 1, 2, 3. There we go. Okay, double check here. So we're going to take x cubed as my parent, and then we have x minus 2 quantity cubed plus 3. Graph it, and there it is. It's shifted up. Okay, let's do a negative. So let's say y equals negative the quantity x minus 1 cubed minus 2. So we have x minus h, so negative h equals negative 1, h equals 1, so that means 1 to the right. Here we have k is equal to negative 2, which means down, so this is to the right, and this is down 2 units. And this is a reflection across the x-axis. So let's pull this thing back down again. So here it is. Again, you do the reflection first. So we're going to take that and we're going to flip it top to bottom. So that's reflecting it across the x-axis. This goes down to there. Then we shift to the right 1 unit, and then we shift down 2 units like that, and you get that. And then we go check it. So what we have is there's a negative sign out here, and what else did we have? -1, -2. Okay. So subtract 1, x minus 1, -2, graph. Okay, so there you actually can see it. Looks good. Okay. Now if you had a negative sign, so that I guess the third case is if you have a negative sign out inside. So how does that work? So let's say you have negative x plus 3 cubed plus 1. So again, what you're going to do is you have to factor out a negative sign out of both terms that are in the parentheses. So that'll be x minus 3, negative the quantity x minus 3 cubed plus 1. So this means a y reflection. This means you've got x minus h. So negative h equals negative 3, or h equals 3. So that's going to be to the right 3 units, and this one is the k, which is k is equal to 1. So that means up 1, and this means y-axis. So we take, let's go back here and get everything back the way it was. So we put that over the parent function. So the y-axis reflection is we flip it from left to right. So there we go. It actually looks exactly like if we flipped it across the x-axis. And then we move it 3 units in the x direction. 1, 2, 3 units, and up 1 unit. Like that. And then we go over here. And so the negative sign is inside. And what do we have? We had x, what was the one? Negative x plus 3. Okay. Plus 1. Plus 3 plus 1. Negative x plus 3 plus 1. And we graph that. And there we go. Except I don't think I did the equation right. What was my equation? Oh, it was 3, not 1. Okay, so that should be plus 3, not plus 1. Graph. Okay, there we go. So you can see how that works. Okay, so we've talked about translation in the x and y directions. We talked about reflecting across the x and y axis. Those are all pretty easy because you keep the original shape. In terms of, I always want to say stretching and shrinking. So when you have a constant in front of the function, the parent function, if this constant is greater than 1 and positive, then what it does is it stretches it. And if this constant is between 0 and 1, you shrink it. Now if it's negative, you would do an x-axis reflection as well, but in terms of the numbers. So it's different though when you do it when it's inside the parentheses. You actually shrink it in the x direction horizontally, which kind of horizontally stretching means vertical shrinking to some extent. I mean, actually, did I say that right? Horizontal stretch is like a vertical shrink and the opposite. So, yeah, here it says for polynomials, a vertical stretch is the same as a horizontal shrink, and a vertical shrink is the same as a horizontal stretch. So, I didn't even talk about that. So let's talk about it. So, these are polynomials, and so we were saying this is a vertical stretch. So let's think about that. Let's draw a axis, and we'll just draw a quadratic equation. Y equals x squared. So it's the origin, and it increases more rapidly as you go further away. Okay, so that's my attempt at drawing a parabola. So the top one is, this is a vertical stretch. So what that means is you're stretching it vertically. So how would that look? So it would mean it increases more rapidly as you go to either side of the origin. So you're basically pulling it, stretching it like that. But you can see a vertical stretch is causing it to go horizontally shrinking. So that's what they're saying. So if you go the other way, if you shrink in the y direction, your y value for given x is less. So this is vertically you're shrinking it, it's getting smaller, but horizontally you're stretching it. So that's the whole concept. And one way to think about it is, if I have, let's say I have the function 3x squared. Another way of doing that would be to, that's the same as the square root of 3 squared times x squared. So if you square the square root of 3, you just get 3. Now these are both have the same exponent, so you can combine them. So you get the square root of 3x quantity squared. So this is outside the parentheses. This is inside the parentheses. In both cases, the square root of 3 is greater than 1, and 3 is greater than 1. So when you have a number here that's between 1 and infinity, whether you move this constant inside or you leave it out, you're still doing the same thing. You're still stretching. You're still deforming it in the same direction. So the question is, how do you know how much to shrink something or stretch something? So let me add a page here. What we'll do is we'll plot y equals x squared. So here's y equals x squared. Plot that thing. Okay. So let's take a picture of that. So let's say let's look at the case of two cases here. Y equals 2x squared. So that's a vertical stretch. So what happens is, for a given value of x, the height is going to be twice as much. So the way we could do that is just go to a value of x, see what the y is, and then just double it. So instead of 1, it'll be 2. Here, instead of 4, it would be 8. Instead of a half, or actually here it would be a quarter. So instead of a quarter, it's a half. Instead of negative 1/2, it'd be, instead of a quarter, it would be a half. And here you double it. So, you just have to scale a few of the numbers and just make it bigger like that. Now, when it comes to going the other direction, now I could rewrite it. This is, y equals the square root of 2x quantity squared. And what would happen is you would move it this direction a factor of 1 over the square root of 2. So this distance here relative to this distance horizontally would be equal to 1 divided by the square root of 2, I think. But let me just copy this graph, put it in one more page. I'm just going to, instead of doing y equals 2 times x squared, it's going to be 2x quantity squared. So in this case, what you're talking about is you're going to move these points half the distance to the y-axis. Here we double the distance from the x-axis. So because this is a number greater than 1, this is a horizontal shrink, so we're going to shrink in this way. So here, if it's a 1, then we go to a half. Here it's 4, so we go to 2. And same way on the other side. Here we go from -1 to -1/2. Here we go from 4 to 2 to, sorry, this goes from 2 to 1. This goes from 2 to 1. And so it looks like that. And so we're shrinking in the x direction, but you can see that we're actually stretching in the y direction. And another way to think of this is, another way to write y equals 2x quantity squared is we can square the 2. So that's 2 squared times x squared, and 2 squared is 4. So you get 4x squared. So these two equations are equivalent to each other. And in this case, we're stretching by a factor of 4 in the y direction. So here we go from 1/4 to 1. That's 4 times. Here we go from 1 to 4. Here we go from 4 to 16. So you're either shrinking this way by a factor of 2, or you're stretching this way by a factor of 4. And when you're dealing with things like square roots or reciprocals, it's not quite so simple. I mean, the general direction of things is going to be the same. Let's look at a reciprocal function just to give you an idea of how that works. So if I plot 1 over x, so there it is. And I'm just going to draw the picture to see what happens here. So so that was 1 over x. So now what happens if I do f of x equals 1 over 2x? So there you can see that since I'm multiplying, this is kind of like this one. So I should shrink it in the x direction, but it's going to look different. So let's just see what it looks like. So I'm going to, if I do 1 over 2x, actually 1 over, I'm going to put it in parentheses or it won't do, right? Okay, now graph it. Actually it does. Okay, so it does push it up against here. So this point goes from 1 to a half. This point would go from 2 to 1. So we are shrinking it just like we did. So a coefficient here. You also, so are we stretching it in the vertical direction? Not really. Okay, so you can see from a shrinking standpoint it makes sense, but in the vertical direction it doesn't. And that's because you can also think of this as, instead of 1 over 2x, you can think of it as 1/2 times 1 over x. So what we're actually doing here is the coefficient in front of the parent function is 1/2, so we're actually shrinking it in the y direction. Whereas here, because they were both in the numerator, or they both, this here you have it, the multiplied by the parent function is in the denominator. Here they're both in the numerator. So what happens with this reciprocal function is it shrinks in the x direction, but it also shrinks in the y direction. And you can see if I say 1 over 10x, it's going to really shrink. It's going to be really close to the x-axis. So it gets, it's going to be moved 10 times here, this direction, 10 times down.